Hello, and we are going to talk through the solutions. This is my PDF of all of my extra notes written on top of the class notes for Chapter 1, Section 2, Part B, so the last little bit of Section 1.2 of our textbook. So we've talked about lots of different properties of functions, so now we're going to look at a few more. Specifically, there are three major types of symmetry that we look for in graphs. The first is symmetry with respect to the y-axis. And what that means is that if you were to fold it in half along the y-axis, the two sides match. Or if you were to take your picture and just flip it 180 degrees and rotate it around the y-axis, your picture would be exactly the same. So that's what I did here. I took this JPEG picture and I flipped it over, and you can see they're the exact same. So symmetry with respect to the y-axis. Symmetry with respect to the x-axis is similar, only you would flip your picture around the x-axis. And then the third type of symmetry is symmetry with respect to the origin. So that is, you want to think about that as doing a 180-degree rotation. So you put your finger on the origin and you spin your picture upside down. And if it is the exact same upside down as it is right side up when you've spun it, and I indicate spinning because a lot of times people think about symmetry with respect to the x-axis as being the upside down because you've just flipped it over the x-axis. So symmetry with respect to the origin means rotating it at 180 degrees. Now, what you see here is a cubic function. The reason why it's symmetric with respect to the origin is because it factors nicely into x times x minus 2 times x plus 2. And so you can see it's got roots at 0, -2, and +2. If you took that cubic function and shifted it up even just 2, then you get this picture. And if you spin that upside down, it is not the exact same graph. So cubic functions, the vast majority of them are not symmetric with respect to the origin. Some are, but not all. Similarly, parabolas or fourth degree polynomials may be symmetric with respect to the y-axis if their vertex is at 0 when x is 0. But if they're shifted, then they won't necessarily be symmetric with respect to the y-axis. So with respect to the y-axis and the origin are two special symmetries, mainly because if you look at what being symmetric with respect to the x-axis is, that's not a function, right? You can't be a function if you're symmetric with respect to the x-axis because you would fail the vertical line test. So symmetry with respect to the y-axis, we call that being even. And so a function is symmetric with respect to the y-axis if f of negative x is equal to f of x. So again, look over here. It basically means that when x is half, right, down here, that's the same as when x is -1/2, right? So when x is something and x is negative something, they're going to have the same y values. Over here, when x is, say, 2, you're up here at y. Well, when x is -2, you're up at the same y. That's even. And when you are odd, symmetric about the origin, f of negative x is equal to negative f of x. So again, what does that mean? F of negative x. So for instance, let's think about maybe -1-ish here. F of -1 is this, is 3-ish, right? But f of 1-ish, right? Come over here, f of 1-ish is -3-ish. So -3-ish. So they're the opposite signs. That's what we call odd. Again, I said a relation symmetric with respect to the x-axis is not even a function. So in the first example, we look at determine if the function's even, odd, or neither, confirm with a graph. And so to determine if it's even or odd or neither, you use these algebraic definitions of being even. and being odd. So you're going to plug negative x into your function and see if that matches your function identically, it's even. If it is the opposite sign of your function, then it's odd. And if neither one of those two things is true, then it's neither. So, for example 1 here, for a, f of x equals 7 over 5 minus x squared. If you plug in negative x, well, negative x squared is just x squared, and it's the exact same function, f of x, so we call that even. And we can confirm it with the graph because when we flip it over the y-axis, it's the exact same thing. For part B, and there's my little flipped over picture. For part B, x cubed minus 3, again, based on just the picture, it's not going to be anything. Flip it over the y-axis and it's not going to be the same, or rotate it 180 degrees, it's not going to be the same. And that's what these two pictures show. So it's neither, but how would we show that algebraically? Well, you're going to plug negative x into f, and negative x cubed is negative, so negative x minus 3. But negative x minus 3 is not the same thing as positive x cubed minus 3. So negative x cubed minus 3 is not the same thing as positive x cubed minus 3. So it's definitely not even. And then what is negative f of x? Well, that's negative the entire function. So that's negative x cubed plus 3. That negative distributes. And again, those are not the same, so it's not odd. So it's neither. And lastly, for part C, we had x over x to the 4th plus x squared. So if you plug in negative x, the denominator, because they're both even exponents, the negative doesn't make a difference. So we end up with negative x over our denominator. So it's clearly not going to be even. It's not f of negative x is not f of x. But it is odd because negative f of x is just negative x over x to the 4th plus x squared. So it's odd. And again, you can see in the picture, if you were to rotate it 180 degrees, it's exactly the same graph. All right, so notice that an odd function must contain the origin if its domain contains 0. Explain why. Well, in this example here, notice 0 was not in the domain. But if we go back and look at our first odd example, this special cubic right here, x equals 0 was one of its roots. It did contain the origin. And again, algebraically, how can we prove that that must be true? So an odd function means that f of negative x must equal negative f of x. Let's say f of 0 is some number y. Let's pretend for a moment that it's not 0. So it's not at the origin, right? Then f of negative 0, well, negative 0 is just 0. Well, f of 0 is y. Okay, but if the function's odd, then f of negative a number must equal negative f of that same number. Well, f of 0 was y, so negative f of 0 must be negative y. Okay, but then that means, because we already said f of negative 0 was y, we already said that this was y, then that means y has to equal negative y. But if I add y to both sides, then I'm going to have 2y equals 0, and this implies that y is in fact 0. So f of 0 is 0, the origin. Any odd function that contains 0 in its domain must map that 0 to 0. So when you spin it around 180 degrees, it's at the same spot. So origin is there. When we are approaching different values of x, we talk about approaching x from the right or above. So from the right, so if c is right here, let me show you here. If c is right here on my number line, if we are kind of tracing our function going this way, that's as x approaches c from above or from the right. If we are going to write, if we're looking at values of x approaching c from the left, right, that looks like this. If the values of x are approaching c from both above and below, from both sides, we just write x approaching c. That arrow means approaching. If x is increasing without bound, that basically means x is going to positive infinity. X approaches positive infinity. Or x approaches negative infinity. It decreases without bound. So I'm going to introduce a little bit of limit notation to you right now. So the function, if the function values f of x, so these are the y values, if they approach a value of, say, 1 or 5 or 10 or any number, but if they approach some number, we write that the limit of f of x equals 1. Or again, you could say f of x approaches 1. If the function values of f of x increase without bound, then we say the limit of f of x is infinity, right? Or f of x goes to infinity. Similarly, if they decrease without bounds, if y goes down without bound, right, f of x goes to negative infinity. Thus, this is a little bit of intro to calculus, really. This notation right here, the limit as x approaches 2, the limit of the function as x approaches 2 equals 5, means that as x approaches 2 from both the right or from the left. So it's kind of like you've got this picture. Here's my function, and if I'm approaching 2 from above 2, what are my y values doing? My y values are going down to 5. And if I'm approaching 2 from below, from the left, my y values are also approaching 5, right? Then the y values approach 5. That's what this limit notation means. All right, so example 2, determine the behavior of the function x divided by x cubed minus x squared minus 6x, and then confirm graphically. So I'm going to only look at the graph to do this rather than confirm graphically. I'm just going to look at the graph because that's a little bit quicker. What you can see here, though, is your x will divide out when you factor it, and so this function is going to have a hole at 0. So when x is 0, the hole is at the point 0, and then you plug 0 in for what you've simplified. So 0 minus 3 times 0 plus 2, that's going to be negative 1/6. So in this picture, there's actually a hole right here, even though it's hard to see. So as x approaches negative 2 from the left, okay, so here's negative 2. So from the left, I've color-coded this all to make it easier to see. So trace along that graph. Take your finger and trace the function and move toward x equals 2, but trace your finger along the y values. Well, as you trace along the function for the y values, as you get closer and closer to negative 2 from the left, your y values blow up to infinity. So we actually write this as the limit as x approaches negative 2 from the left is equal to infinity. The limit of my function, the limit of my y values as x approaches negative 2 from the left is infinity. What about negative 2 from the right? Above 2. So again, above 2, where's my function? Well, where are the y values? Well, they're down here. They're down there. And they go down toward negative infinity. So the limit as the limit of f of x as x approaches negative 2 from the right is negative infinity. What a and b together mean is that the limit as x approaches negative 2 does not exist because it's not the same on the right and the left, right? They're going opposites. For c, as x approaches 0 from the left, well, that limit is approaching that hole at negative 1/6. The limit as x approaches 0 from the right, again, that's also going to the hole, negative 1/6. So together, this means the limit as x approaches 0, the limit of my function as x approaches 0, it exists, and it is this number, negative 1/6, even though there's not an actual defined value there. The function is not defined at 0. There's a hole. But the limit exists. When the limit exists, it means they're coming the same place. They're going to the same point. All right, and so then likewise for 3, as x approaches 3 from below, from the left, it's going down to negative infinity. And then as x approaches 3 from the right, from above, it's going to positive infinity. And end behavior. As x approaches positive infinity, as x grows without bound, your y value is actually shrinking and shrinking and shrinking towards 0. So you've got a horizontal asymptote there. And as x approaches negative infinity, likewise, f also goes to 0. So horizontal asymptote at y equals 0 for this example. So in this example, it has vertical asymptotes at -2 and 3 because the function values increase or decrease without bound as x approaches -2 or 3. And similarly, it's got a horizontal